Hi everybody. Start stream. Okay, it was going. I think it's going. Um, yeah. It's not going. I think it's going. No, sure. Hi everybody. I'm not sure if this is going. I'm pretty sure it is. Kind of new to this live streaming, but anyway, welcome back to Dave's Math Channel. As promised, I'm doing my second live stream on this channel. This one's on the golden ratio, and I think this one's gonna be pretty short. I apologize for being late again. It's taking me longer to make these than you might think. Anyway, let's just begin. So first, I'm going to define the golden ratio. I'm sure probably most of you have probably seen this before, but the way the golden ratio is usually first defined is in terms of this thing called the golden section. So we're just supposed to imagine that we have a line segment, an arbitrary line segment, and we want to divide it into two subsegments, which of length A and B. And we want to do this in such a way that the ratio of A to B is the same as the ratio of the whole length, which is A plus B to A. So in other words, the ratio of the length of the line segment to the length of its longest subsegment is equal to the ratio of the length of the longest segment to the length of the shortest segment. Another way to say that algebraically is that A over B, that's just the second ratio I mentioned, ratio of the longest segment to the shortest segment, is equal to the length of the whole segment, A plus B over A. And it turns out that there's a unique irrational number called phi, or the golden ratio, that is equal to that ratio. It's approximately 1.618. Okay, so now I've just kind of defined the golden ratio. And you might wonder, can you calculate its exact value? And it turns out you can. It's not even really that hard to do. So we can turn this into an algebra problem. And there's no reason we have to use A and B. We can scale this thing. So I think it's most convenient to let B equal 1 and A be the golden ratio, phi. Uh, and so then the golden ratio is the thing we're calling phi. That's phi to 1. A to B is phi to 1, or phi. And that's also equal to phi plus 1 over phi. Um, and so you would do a little bit of algebraic manipulation on this first equation, and you get phi squared equals phi plus 1. If you just multiply both sides by phi, that's what you get. And you can turn this into a quadratic equation. Phi squared minus phi minus 1 equals 0, just by subtracting phi plus 1 from both sides. And I think you guys probably know how to solve quadratic equations. You just apply the quadratic formula. And if you do that, you'll find, in this case, A is 1, B and C are both negative 1. And if you apply the quadratic formula, you'll find that phi is equal to 1 plus or minus the square root of 5 over 2. But it's not 1 minus square root of 5 over 2 because that's negative. And we know the golden ratio is positive. So the only positive root is 1 plus square root of 5 over 2. And you can calculate this as accurately as you want. It's very easy to calculate square roots. And I wrote down the first 10 decimal places here. 1.61803398887. And of course, it goes on forever. But anyway, so it's a very important mathematical constant. It's probably one of the top five, I'd say. I mean, in terms of irrational constants, pi is probably the most well known. Most people seem to think that's the most important mathematical constant. E is another big one. B used to be called the base of natural logarithms. Now it's called Euler's constant. Usually don't learn about that one until calculus. So I think most people don't know about E, but it's considered the second most important irrational constant by most mathematicians after pi. And then V, maybe the third most important. I don't know. I mean, it's kind of a matter of taste. A lot of people like the square root of 2. But V is definitely up there. It's definitely a very important number in math. So And why is it important? Well, there's a lot of reasons. It comes up in a lot of contexts. I'm just doing a few of them in this video. But in the last live stream I made, I talked about Fibonacci numbers. Well, it turns out the golden ratio is very closely related to Fibonacci numbers. I think I mentioned that in the previous live stream, but I didn't say how. And it turns out that the way they're related is if you take ratios of two consecutive Fibonacci numbers, which is done in this table here. This table has the first 30 ratios, Fn over Fn minus 1 for n going up to 30, I believe. And you'll see that these ratios approach the golden ratio. Um, the first one isn't very close, 1, 1 over 1. But then you get 2 over 1, yeah, and then you get 2 over 1, which is 2, 3 over 2 is 1.5. It converges. I mean, this is an exponentially convergent sequence, but it converges sort of slowly. I mean, all exponentially converging sequence converge very rapidly, but you'll probably see other ones that converge a lot faster than this one. But by the time you get up to the 30th ratio here, it's already correct to, I think, all the decimal places shown, or at least most of them. I think at least the first 10 decimal places, all the ones I showed you earlier. So, that's how Fibonacci numbers are related to the golden ratio. Pretty remarkable. You can actually prove this because there's a formula. I think I even went over this one last time too. There's a very useful formula called Benet's formula, which is a exact formula for the nth Fibonacci number. It turns out it's in terms of the golden ratio. F sub n, this is Binet proved this, I believe, in the 18th century. He was a French mathematician. He proved that the nth Fibonacci number, F sub n, is equal to phi to the nth power minus the quantity negative phi to the minus nth power, all over square root of 5. And if you want to write it out in terms of radicals, it's just the expression on like 1 over square root of 5 times 1 plus square root of 5 over 2 to the nth power. That's just phi 1 plus 5 over square root of 5 over 2. And then minus 1 minus 5 over square root of 5 over 2 to the nth power, and that thing is minus 1 over phi. And when n is large, the term on the right goes to 0 pretty quickly. That's kind of easy to see because its absolute value is less than 1. Like I said, 1 minus square root of 5 over 2 is minus 1 over phi. Phi is about 1.618. It turns out 1 over phi is also phi minus 1, 0.618. So the quantity on the right is minus 0.618. If we take a really large power that, it's very, very close to 0. So for instance, if you were calculating the 100th Fibonacci number, it would essentially be phi to the 100th power divided by the square root of 5, with a very, very small margin of error. And I think from this formula, you can kind of see why the ratio of two consecutive Fibonacci numbers approaches the golden ratio, because, like I said, F100 is very close to phi to the 100th over square root of 5, but then by the same token, F99 would be very close to phi to the 99th power divided by square root of 5. Take the ratio of those two things, you get phi. Phi to the 100th over square root of 5 divided by phi to the 99th over square root of 5. The square root of 5's cancel, and you're just left with phi. Of course, there is a very small error due to the term on the right, but that error goes to 0 as the indices get large. So that kind of proves that the ratio of two consecutive Fibonacci numbers approaches the golden ratio. Anyway. And then I think I talked about this last time, the golden rectangle. I just kind of glossed over it. I said what it is. I didn't really explain it in that much detail, but I'll just say it again. The golden rectangle is a special rectangle. It's a rectangle whose dimensions or whose aspect ratio is phi to 1. So if you like, it's A to B. A golden rectangle is any rectangle whose dimensions are A by B, where A and B form a golden section. In other words, A is phi times B. So now that's just another way of saying the aspect ratio is golden ratio 1.618. And I think I talked about this a lot in the last live stream I made. This seems to me the most aesthetically pleasing aspect ratio. I think nowadays most big screen TVs are very close to this ratio. The old TVs weren't; they were more like 1.3 to 1. I think most movies you see the aspect ratio is close to the golden ratio, and that seems to be more pleasing. And you can see a lot more with a good, a longer aspect ratio than getting your TV. That's why you watch a lot of old movies on TV, and they pan the screen so it could fit the old TVs. Now you don't really have to do that anymore. And why is the golden rectangle special? I talked about this last time. There's something called the golden spiral, and here's a detailed, um, kind of illustration of construction of the golden spiral. I might as well go over this. So the remarkable thing about the golden rectangle, I think I talked about this last time. You can keep partitioning into smaller and smaller golden rectangles. I mean, you start with a whole big golden rectangle, but then you can you I think they showed this in a previous slide. There's a very faint partition. There's a square, so you can partition the golden rectangle to a square and a similar golden rectangle on the right, except it's turned sideways. And then you can keep doing this infinitely many times. And that's kind of what they're showing in this picture. And this picture kind of sums up the whole construction of the golden spiral. So you're supposed to imagine that first they're partitioning the golden rectangle into, smaller and smaller golden rectangles. And you can keep do this, until the cows come home. I guess ideally you would do this infinitely many times. Of course, nobody can do anything infinitely many times because we're finite beings and we have a finite lifespan. But you can just imagine you can do it a large number of times. I think we just did it like 10 times essentially. It looks like it's almost going to infinity. But then what you do once you've made all these squares is you draw the quadrants of circles. So for instance, if you look at the first square, the biggest square in this picture, that's the square on the left. You just draw this quarter circle, this circular arc that starts in the lower left corner and goes up to the upper right corner, and then you keep doing the same thing for each of the following squares, and you keep continuing the spiral in this way. And when you're done, you get this really nice picture. It's essentially a logarithmic spiral. And I think last time I talked about the Fibonacci spiral. The Fibonacci spiral is a approximation of a golden spiral. You start with a very small square in the middle of side like 1, and then you use Fibonacci number side, squares. That'll give you an approximation of the golden spiral, but not exactly this golden spiral. If you really want to construct the golden spiral, you have to do it this way. You don't use Fibonacci numbers, you just use the golden ratio. So anyway, that's the golden spiral. Pretty beautiful construction. And I think I mentioned last time that the chamber nautilus has a shell that looks almost exactly like this. Not quite, but it's a logarithmic spiral that's very close. Looks very close to this golden spiral. And I'm just gonna finish this pretty quickly. I would have liked to have done more. There's a lot of uses of the golden ratio in nature. I didn't really prepare that. I talked about that a little bit in my last live stream. I talked about how flowers have Fibonacci numbers of petals most of the time. And there's also an economical reason in terms of the golden ratio why that's the case. I wish I'd had time to prepare that. But it turns out if you look at the angle, I'll just say it. I don't have a slide on it, but it turns out that if you look at flower petals or leaves on a branch, the each successive leaf is rotated with respect to the previous one by an angle that's equal to approximately 360 degrees divided by phi squared, or about 137.5 degrees. And it turns out that that arrangement gives it the maximum amount of sunlight, the maximum amount of exposure to sunlight. You can actually prove that. And that's the reason why plants, flowers and leaves on plants have Fibonacci numbers of leaves. going clockwise and counterclockwise anyway. I just thought I'd mention that. But now I'm just gonna sum this live stream up by talking about how the golden ratio has been used in various works of art and in architecture. Here's some. These are five famous works of art. I think you probably recognize most of these. The three on the left are all by Leonardo da Vinci. He was he knew a lot of math. Leonardo da Vinci, he's considered one of the greatest painters of all time. I'm sure you guys all know he's done some masterpieces. Three of them shown here: the Mona Lisa on the left, and then the Last Supper on the top middle, and then right below that, the Ascension. And you can see how he used the golden ratio in each of these works of art of his. And I believe was deliberate. He was a mathematician, and I think one big reason why so many people consider the Mona Lisa so beautiful is because he used the golden rectangle multiple times in different parts of her body in the picture. I mean, her head, the ratio of the height of her head to the width is the golden ratio. The ratio of the if you look at the distance from the top of her head to where her hands are, you take that ratio to the side of the left side of her head all the way to the right side of the picture. That's also a golden ratio. You can see where he uses it. This picture uses it multiple times. And I think that gave her a really beautiful appearance in this picture. I'm sure that's a big reason why everybody considers her so beautiful because their proportions are just right. Um, and similarly, the Last Supper, that's the one in the top middle. I don't think he used a golden spiral. I mean, he used a golden spiral for the Mona Lisa, but he also used it in the Ascension, bottom right. But he didn't use it specifically in the Last Supper, but he did use the golden ratio. I mean, you can divide the Last Supper in a bunch of golden rectangles, which I think is shown on this picture. I don't know if you can see the lines on the top, the middle picture, but the lines show various proportions in the Last Supper where the golden ratio is used. So those are just three of Leonardo da Vinci's works of art that involve the golden ratio. But it wasn't just him who used the golden ratio. Supposedly Michelangelo did too. I never heard that Michelangelo was a mathematician. Maybe this was just kind of incidental. I don't know, but they do show a golden spiral on the top right picture. That's the Sistine Chapel picture, and they show how the golden ratio fits into that one. And then the one on the bottom right, I don't know the title of this. This is a pretty famous Japanese painting, I think from the 17th century. It's a picture of a tsunami, and the kind of spiral shape of the wave is a very close approximation of the golden spiral. It turns out, and I don't know if that was deliberate either. I think there's a lot of mathematicians who like to analyze works of art and they show where the golden ratio or the golden spiral fits into them, but I don't know if the art that means the artist specifically were using it or not. But it kind of looks like they did. So I mean, this is just kind of indicates how the golden ratio is important in aesthetics of various works of art, and not just art, but architecture as well. And here are five famous buildings throughout history. The top left one is the pyramid, one of the Great Pyramid with the Sphinx in front. And you can see the golden spiral on that one. And then the top middle, I believe this is the Notre Dame Cathedral. I just learned this today, but apparently the golden ratio was used in its architecture too. Again, I don't know if that was deliberate or not, but and also the Taj Mahal. You can see where the golden rectangles are. And the Parthenon, I believe that was deliberate, the lower left one. The Greeks knew a lot of math, the ancient Greeks. I'm pretty sure they knew about the golden ratio. They knew about square roots. So they were pretty good mathematicians. As a matter of fact, they used to do some geometric constructions. I think Euclid came up with a method of doing geometric constructions with compass and straight edge. And one of the things he was able to construct was the pentagram, or equivalently the a regular pentagon. I probably should have shown this one as well because the golden ratio fits into the geometry of a regular pentagon and a pentagram. And I wish I'd shown that. I didn't. But anyway, like I said, my time was limited today preparing this video. But at least here's a picture of the Parthenon, and you can see how the golden ratio fits into its geometry. The ratio of the width of the Parthenon to its height is approximately the golden ratio, and it's also used several other places. And finally, you guys might be surprised to learn this, but the United Nations headquarters, which I believe was built in 1945, that one also involves the golden ratio in its architecture. As a matter of fact, it involves it 3 times. So there's 3 golden rectangles on the side of the UN building, and you can see them in this picture. And I believe that was delivered as well. So anyway, those are just some examples of how the golden ratio, appears. And I guess there's a lot more I could have said about it. Maybe I'll do that in my next live stream. Anyway, that's all I prepared for tonight. So thank you for watching. Long live math, and I'll see you guys next.